By 2028, 80% of infrastructure spending will go toward inference, not training. It's a fundamental shift in how AI infrastructure gets built. The infrastructure requirements for training are completely different from inference. Different hardware, different power profiles, different networking, different cooling, different economics. This is the training to inference shift. And if you're involved in AI infrastructure, whether you're architecting it, buying it, or investing, understanding this explains where the industry is heading and why data center designs are evolving the way that they are. Let's start with first principles. What are training and inference? Why are they fundamentally different? Training builds the models. You take massive data sets, that'd be text, images, video, code, and run them through neural networks repeatedly, adjusting their weights and parameters until the model learns patterns in the data. Training is computationally intensive. It requires massive parallel processing across hundreds or thousands of GPUs. And it happens once or periodically when you retrain or fine-tune the model. Inference uses the trained model to make predictions. A user types the question into ChatGPT or Gemini or Claude. The model processes that input and generates a response. That's inference. A recommendation engine suggests products. That's inference. An autonomous vehicle identifies a pedestrian. That's inference. Training happens in batches, typically offline in controlled environments. Inference, well, that happens continuously in real time, millions or billions of times per day, every time someone interacts with the AI system. Training is a batch workload. Inference is a real-time, user-facing workload. That fundamental difference changes everything about the infrastructure you need to support it. Gartner projects that spending on servers for AI inference will grow 42% annually through 2028. Training server spending 24% annually. That's a massive gap. And by 2028, over 80% of AI infrastructure spending will support inference workloads, not training. Why the disparity? Because training happens once, inference happens continuously. A single trained model like GPT-4 or Claude or Gemini gets trained once over weeks or months. But that model then runs billions of inference operations. Every ChatGPT query, every API call, every time someone uses the model, that's an inference operation. As AI deploys across more applications, customer service chatbots, content moderation, recommendation engines, code generation, fraud detection, medical diagnosis, the volume of inference operations explodes. Training creates the model. Inference is where the model generates value at scale. That's why infrastructure spending will shift heavily toward inference. Let's break down why inference requires fundamentally different infrastructure. We'll start with latency. For training, latency matters, but in comparison, not as much. You're running a batch job. The model trains for hours, days, or weeks. If a single gradient update takes 10 milliseconds or 50 milliseconds, it doesn't materially change the outcome. Now, in some of my other videos, you've heard me share about techniques and technology to reduce latency in training because you want to get as much as you can out of the GPUs for the money you're paying. However, the job will complete when it completes. Infrastructure that's not tuned to the minimum latency does not materially change the outcome. For inference, latency is everything. In the world we live in now, Google flags a website that does not fully load in 2 seconds. User experience is not considered good. Now think about in the AI world. A user types a question or waits for a response. If the inference latency is 100 milliseconds, the experience feels instant. If it's 500 milliseconds, it feels sluggish. If it's 2 seconds, users are done. They abandoned the interaction. And this isn't just about user experience, it's about economics. In high volume inference scenarios, every millisecond of latency reduction means you can handle more requests per second on the same hardware. Lower latency equals higher throughput, which equals better unit economics. So inference infrastructure optimizes for low latency. That means fast GPUs or ASICs, low latency networking, optimized model serving frameworks, batch strategies that balance latency with throughput, memory architectures that minimize data movement. So training optimizes for raw compute throughput. Inference optimizes for latency first, then throughput. Now let's talk availability. Availability requirements differ just as dramatically. Training is batch-oriented. If a training job fails, the GPU crashes, a network link goes down, a power supply fails, you checkpoint and restart. It's annoying, but it's not a user-facing failure. No one, well at least not millions of people, are waiting on the training job to complete in real time. Inference is user-facing. If your inference system goes down, users can't access your AI features. Your chatbot stops responding. Your recommendation engine goes dark. Your fraud detection system fails. That means inference infrastructure needs production-grade reliability, 99.9% uptime minimum, and often 99.99% or higher for critical applications. Achieving that requires redundancy, multiple inference servers behind load balancers, failover mechanisms, health checks and automatic traffic rerouting, monitoring and alerting, disaster recovery plans. You design and build inference infrastructure the same way you build production web services, because that's what they are. Hardware requirements tell an interesting story about the training to inference shift. Training needs maximum parallel compute power. NVIDIA H100s, Blackwell GPUs, AWS Trainium, whatever the latest generation offers, because training is about processing massive datasets across as many tensor cores as possible, as fast as possible. The latest GPUs aren't just faster, they're dramatically more power efficient for training workloads. An H100 delivers roughly 3 times the training performance of an A100 at similar power draw. So for training, you want the newest, fastest hardware. Inference is different. You're running a forward pass through the model. No back propagation, no gradient calculations, no all reduce. The compute requirements are lower. And that opens up interesting hardware options. Older generation GPUs can handle inference effectively. An A100 or even a V100 can serve many inference workloads that would be too slow for training. The performance per dollar is often better on previous generation hardware once the newest GPUs command a premium for training workloads. Custom ASICs designed specifically for inference, like Google's TPU inference accelerators or AWS Inferentia. They can deliver better performance per watt and performance per dollar than general purpose GPUs for inference, because they're optimized for the specific operations inference requires, like matrix multiplications, activation functions, layer normalization. No need for the full flexibility of a training GPU. There's also a growing category of inference optimized GPUs. NVIDIA's L4 and L40 chips, AMD's MI210s. These are designed specifically for inference workloads. Lower power consumption, optimized for lower batch sizes, better inference throughput per dollar. The economics matter here. If you can serve inference on hardware that's 50% cheaper with only 20% lower performance, your unit economics improve dramatically at scale. And this is why you're seeing inference teams split their hardware procurement. Latest generation GPUs, for training clusters, inference optimized hardware for serving their users. Let's talk about the impact on power and cooling. Power profiles differ in ways that complicate infrastructure planning. Training clusters run at full load constantly, 60 to 100 kilowatts per rack, sometimes higher with liquid cooling and dense GPU configurations. But the load is predictable. You're running compute 24/7. The GPUs are pegged at 100% utilization. That makes power and cooling straightforward, in the sense that you know exactly what you need to provision. If your rack draws 80 kilowatts, you provision 80 kilowatts of power and cooling capacity, and you're done. Inference is variable. During peak hours, daytime in users' time zones, you might be at 80% or 90% utilization. During off-peak hours, you might drop to 30 or 40%. Weekends might be different from weekdays. The load follows user patterns. That variability creates challenges. You can't just provision for peak load and ignore efficiency. If you provision cooling for 80 kilowatts, but you're only drawing 20 kilowatts during off-peak, you're wasting energy on overcooling. So inference infrastructure benefits from dynamic power management and adaptive cooling, scaling compute up and down based on demand, modulating cooling systems based on real-time thermal load, auto-scaling inference servers. Now, with that said, by 2026, many inference deployments will still hit 30 to 100 kilowatts per rack. You're not going back to traditional air cooling. Liquid cooling or advanced air cooling with containment remains necessary. But the way you manage that cooling dynamically based on variable load differs from training clusters. Okay, now to the edge. Here's where inference gets even more interesting. Gartner projects around 20% of AI inference spending going toward edge deployments by 2026. Why edge? Latency. For some use cases, the round-trip time to a centralized data center is too long. An autonomous vehicle can't send sensor data to the cloud, wait for inference, and get a response back. The vehicle needs to make decisions in microseconds, or at least single-digit milliseconds locally. Real-time video analytics, augmented reality, industrial automation, medical devices. These applications need inference to happen at the edge, close to where the data is generated, with minimal latency. So inference infrastructure is splitting into two categories. Centralized inference, large data centers with hundreds or thousands of GPUs or ASICs serving high-volume inference for latency-tolerant applications. Think ChatGPT, content recommendation, image and video generation. I mentioned fraud detection. These can tolerate 50 to 200 milliseconds of latency. Edge inference, smaller distributed facilities closer to the end users or data sources, serving latency-critical applications. Smaller form factors, lower power consumption, different cooling solutions, often using inference-optimized chips rather than full-power GPUs. The edge creates different infrastructure challenges. You're dealing with physical constraints, limited space, limited power, limited cooling capacity. You can't put a 100 kilowatt rack in a retail store or a factory floor. And you're dealing with distributed management challenges. If you have 100 edge locations, each with inference hardware, you need centralized orchestration, remote monitoring, automated updates. It's a different operational model than managing a single centralized data center. The edge also creates interesting hybrid architectures. You might run latency-critical inference at the edge, but send back data to central data centers for model retraining, analytics, and long-term storage. And now to my favorite, networking. Network traffic patterns tell you a lot about the infrastructure shift. Training generates massive east-west traffic, GPU to GPU communication, collective operations like all reduce, where every GPU needs to share data with every other GPU. That's why training clusters use Rocky. InfiniBand, 400 or 800 gigabit Ethernet. You need ultra low latency, high bandwidth fabrics for GPU to GPU communications. Inference traffic is primarily north-south. Requests come in from users or applications. Inference runs on GPUs or ASICs. Responses go back out. There's still some east-west traffic like multi-GPU inference for large models, but the dominant pattern is north-south. That changes your network architecture. For inference, you care more about ingress and egress bandwidth, load balancing across inference servers, and connection handling versus GPU to GPU fabric performance. For edge inference, networking becomes even more critical because you need reliable, low latency connectivity between edge sites and core data centers. Edge sites run inference locally, but need to send telemetry, logs, and raw data back to central facilities for model updates and analysis. So you end up designing hybrid network architectures, high-speed fabrics for training clusters, north-south optimized networks for centralized inference, edge-to-core WAN connectivity with quality of service guarantees for distributed inference. The network design follows the workload, and inference workloads demand different network designs than training. The training to inference shift is really about AI moving from research to production. AI infrastructure investment has focused heavily on training, building foundation models, training massive language models. That's where the innovation was happening. That's where the compute intensity was highest. And we will still see more of that. But now, those models are trained. GPT-4 is trained, Claude is trained, Gemini is trained. The next generation of these are being trained right now. But the real infrastructure growth is shifting to deploying those models at scale. Inference is where AI generates business value. Every customer service interaction handled by an AI chatbot, every product recommendation served to a user, every line of code generated by an AI coding assistant. That's inference. And inference volume grows much faster than training volume. One training run produces a model that serves billions of inference requests. So the infrastructure economics will shift. Training is still important, don't get me wrong. You need cutting-edge training infrastructure to build competitive models. But inference is where the infrastructure spending volume is going. This also changes who's buying AI infrastructure. Training infrastructure gets built by a relatively small number of players, hyperscalers, research labs, and other well-funded AI companies. Inference infrastructure gets deployed much more broadly. Any company running AI applications needs inference infrastructure. SaaS companies, e-commerce platforms, financial services firms, healthcare providers. The inference market is larger, more distributed, and more diverse than the training market. By 2028, 80% of AI infrastructure spending flows to inference. And this will impact and fundamentally shift how AI infrastructure gets architected. Different latency requirements, different availability standards, different hardware economics, different power and cooling profiles, different network patterns, different deployment models with edge infrastructure. Understanding this shift explains why data center designs are evolving, why hardware vendors are launching inference-optimized products, and where the infrastructure growth is concentrated over the next several years. AI infrastructure is transitioning from supporting batch research workloads to supporting production, real-time, user-facing systems at massive scale. That's the training to inference shift. I'm Vernon Neal Reed. This is AI Infrastructure Media.